The winter of 1879 hit different on the northern plains. When the deep freeze struck near the Black Hills, a former trapper turned homesteader watched his neighbor's cabin drop to near freezing overnight after their wood stove died, pipes bursting by dawn, and stored food turning to ice. He had built his own cabin exactly like every other settler was told to build: tight log walls, central wood stove, proven frontier method. But that same brutal cold was defeating homestead after homestead across the territory, families burning through 3 cords of wood in 2 weeks just to keep from freezing, many losing their food stores and livestock water to the cold. Over the next year, this quiet Scandinavian immigrant quietly applied an underground technique borrowed from old trapping wisdom that kept his cabin stable without constant fire. While neighboring cabins dropped below freezing when stoves died, his stayed warm enough to preserve food and keep water liquid, using only 1/3 the firewood. We'll break down the exact steps and numbers behind this forgotten method that every cold climate builder should understand. What did he know about harnessing the ground beneath his feet that everyone else was missing? The Black Hills settlement of 1879 held 23 homesteads scattered across windswept ridges, each family betting their survival on the same trusted formula. Every cabin followed the territorial handbook specifications: single log walls 8 to 10 inches thick, chinked with moss and mud, a stone or brick fireplace positioned on the gable end to draw smoke up and out. The method had worked for trappers and early settlers for decades across the northern territories, and supply merchants from Rapid City to Deadwood stocked their trade routes around it. Cordwood, they assured new homesteaders, remained plentiful in the pine draws and oak groves. A good axe, a steady supply line, and a properly maintained stove would see any family through the worst plains winter. But that winter tested the limits of conventional wisdom in ways the handbook had never anticipated. 3 homesteads on the eastern ridge lost their chimneys when ice dams formed in the flues during a week-long blizzard, filling their cabins with smoke and forcing families to choose between suffocation and freezing. The Hendricks family, newcomers from Ohio, watched helplessly as their cabin's single log walls developed a 1/4-inch gap along the north side when the wood contracted in -30-degree cold, creating a wind tunnel that no amount of fire could overcome. Their youngest child developed frostbite on his hands while sleeping 3 feet from a roaring stove. At the Morrison claim, a different disaster unfolded. The family had stockpiled what they believed was adequate cordwood, but the extended cold snap consumed fuel faster than their calculations anticipated. When their supply ran low in February, they began burning furniture, then floorboards, then parts of their cabin's interior framework. By March, their shelter had become structurally compromised, the roof sagging ominously under snow load that should have been manageable for a properly framed building. The pattern repeated across the settlement with grim consistency. Standard cabins required constant feeding of fuel to maintain interior temperatures above the threshold where stored food would freeze and water would turn solid. When any link in that chain failed, whether through blocked chimneys, inadequate fuel supply, or maintenance lapses, families faced immediate crisis. The territorial supply routes, reliable during milder winters, struggled to keep pace with demand as homestead after homestead burned through their wood reserves weeks ahead of schedule. Into this context of systematic failure came an unlikely innovator whose background bridged multiple traditions of cold weather survival. Eric Larsson had spent 7 years guiding trapline expeditions through Minnesota and Dakota Territory before claiming his homestead, work that exposed him to both indigenous shelter techniques and immigrant building traditions that standard frontier practice overlooked. His family had emigrated from the Hardanger region of Norway, where his grandfather had built stone and timber houses designed to capture and hold heat through months of harsh mountain winters. During trapping seasons, Larsson had observed Lakota winter camps that used earth burming and partially underground shelters to maintain livable conditions with minimal fuel consumption. Unlike his neighbors who saw cabin construction as a straightforward matter of following established patterns, Larsson approached the challenge as an engineering problem that demanded multiple solutions working together. His first deviation from standard practice involved the wall construction itself. Instead of relying solely on 8-inch logs with moss chinking, he built his outer walls with 10-inch logs, then added an inner wall spaced 12 inches inside the first, creating a cavity he filled with tightly packed clay mixed with dried grass and moss. The technique drew skeptical comments from neighbors who considered it excessive labor for marginal benefit. His attention to sealing exceeded anything the settlement had seen. Where standard cabins accepted that some air infiltration was inevitable and even healthy, Larsson systematically identified and sealed every gap, crack, and joint with a mixture of pine pitch, clay, and animal hair that created an airtight envelope. He installed wooden shutters that fit precisely against window frames, eliminating the drafts that plagued most cabins during high wind events. Even his door received custom weather stripping made from beaver pelt strips that formed a complete seal when closed. The community's reaction ranged from mild curiosity to open mockery. Samuel Morrison, whose own cabin would later suffer the structural failures, called Larsson's methods overfussing for a house that needs to breathe. The territorial land agent, making his rounds that fall, dismissed the sealed construction as unnecessary expense that violated common-sense ventilation principles. Fire and cordwood built this territory, he declared to a gathering at the trading post. A man doesn't need to build a fortress when good frontier sense will do. More pointed criticism came from the settlement's unofficial leader, James Crawford, a former military quartermaster who had established the community's first trading post. Crawford viewed Larsson's innovations as a challenge to established order and practical wisdom. A homestead isn't a puzzle to be solved, he announced during a community meeting. It's a shelter to be built the way successful men have built them for generations. When a man starts thinking he knows better than proven methods, he's usually heading for trouble. But Larsson's early results suggested his approach might withstand scrutiny. During November's first hard freeze, when overnight temperatures dropped to 15 degrees Fahrenheit, his sealed cabin maintained interior warmth that allowed him to preserve root vegetables in storage areas where his neighbors' produce had frozen solid. His water supply, kept in wooden barrels near the interior walls, remained liquid, while similar containers in standard cabins developed ice shells that made morning water access a daily struggle. The technical foundation Larsson was building would prove its worth in ways the settlement couldn't yet imagine, but the principles he was assembling challenged fundamental assumptions about how frontier families should approach the problem of winter survival. The earth beneath their feet held thermal resources that conventional cabin design ignored completely, and the techniques needed to harvest that stability required abandoning the fire-dependent methods that territorial wisdom considered unshakable truth. The sealed construction that set Larsson's cabin apart from his neighbors created an unexpected challenge that standard frontier building never had to address. Conventional cabins relied on natural air leakage through gaps and cracks to provide fresh air circulation, but his tightly sealed envelope eliminated those pathways entirely. Without deliberate ventilation, the interior atmosphere would gradually become stale and potentially dangerous. Yet opening windows or doors to bring in fresh air during sub-zero weather would instantly defeat the thermal advantages his careful sealing had achieved. Every cubic foot of frigid outside air that entered would demand fuel to warm it, and every cubic foot of heated interior air that escaped represented wasted energy and precious cordwood. Standard cabins solved this problem crudely through their wood stove operations. The combustion process drew air from inside the cabin and expelled it up the chimney, creating negative pressure that pulled replacement air through whatever gaps existed in the building envelope. This constant air exchange prevented staleness, but also guaranteed that every breath of replacement air entered at outside temperature, placing enormous thermal loads on the heating system. During severe cold snaps, homesteaders frequently found themselves trapped between two unacceptable choices: suffer poor air quality by keeping their shelters sealed, or burn excessive fuel maintaining comfort while fresh air constantly robbed heat from their living space. Larsson's solution emerged from memories of techniques he had encountered during his trapping expeditions. 3 winters earlier, while guiding a survey party through Minnesota's northern forests, he had sheltered with a mixed group of French voyageurs and Ojibwe guides during a prolonged storm. The indigenous members of the party had constructed a temporary winter lodge that remained comfortable despite minimal fuel consumption. and Larsson had noted that their air supply came not from direct openings to the outside, but through what appeared to be a partially buried passage that entered the shelter near ground level. When he asked about the technique, one of the older guides explained that Earth warmed the air before it reached their living space, reducing the shock of cold air intake while maintaining breathability. The concept gained reinforcement from conversations with immigrant families whose old country building traditions incorporated similar principles. Sven Andersson, whose family had arrived from Västergötland the previous spring, described root cellars in Sweden that used underground passages to regulate temperature and air quality. These cellars maintained stable conditions year-round by drawing ventilation air through buried conduits that moderated extreme temperatures naturally. The Earth's consistent temperature below frost depth provided a thermal buffer that pre-warmed incoming air during winter and pre-cooled it during summer. Larsson began his experimental tunnel in late September of 1879, allowing time to complete the work before ground freeze made digging impossible. He selected a location 30 meters northeast of his cabin, positioning the intake where prevailing winds would provide natural air pressure to push fresh air through the system. The excavation required removing approximately 40 cubic yards of soil, following a gentle downward slope of 1.5 degrees to ensure proper drainage and prevent water accumulation inside the conduit. The tunnel construction demanded materials unavailable through standard frontier supply chains. Larsson obtained glazed ceramic pipe sections from a pottery works in Rapid City, each piece measuring 4 inches in interior diameter and 3 feet in length. The glazed surface would resist moisture condensation and prevent organic matter from accumulating inside the passage, while the ceramic material provided durability against freeze-thaw cycles that would eventually destroy wood or metal alternatives. When ceramic supplies proved insufficient, he fabricated additional sections from thick-walled hollow logs, sealing their interior surfaces with pine pitch mixed with animal fat to create a smooth, water-resistant lining. Installation required precise attention to grade and drainage details that conventional cabin building never addressed. Larsson laid each pipe section on a 6-inch bed of graded gravel, ensuring consistent slope and stable support that would prevent settling or joint separation. He wrapped the joints with strips of oiled canvas, then sealed them with additional pitch mixture to create airtight connections. At the lowest point of the tunnel, approximately 15 meters from the cabin, he installed a small drainage chamber filled with coarse sand and gravel that would collect any condensation and direct it away from the air passage. The tunnel terminated inside Larsson's cabin through a carefully positioned opening near floor level on the north wall, the location selected to minimize disruption of his interior layout while ensuring efficient air distribution. He covered the interior opening with a simple wooden grate that could be adjusted to control airflow volume and installed a hinged damper that would allow him to shut off the system completely if necessary. The intake end, positioned well above ground level to prevent snow blockage, received a protective hood designed to exclude precipitation while allowing air entry from multiple directions. Testing began in November as outdoor temperatures dropped toward winter levels. Larsson constructed a simple measurement system using alcohol thermometers positioned at the exterior intake, inside the tunnel at its midpoint, and at the interior outlet. The results exceeded his expectations and challenged fundamental assumptions about fresh air ventilation in cold climates. When outside air registered 10 degrees Fahrenheit, the tunnel outlet delivered air at 43 degrees, a warming of 33 degrees achieved without any fuel consumption or mechanical intervention. As outside temperatures dropped further, the differential became even more dramatic, with the Earth maintaining its moderating effect regardless of surface weather extremes. The system's performance during December's first sustained cold spell provided measurable proof of its effectiveness. While neighboring cabins experienced interior temperature swings of 20 to 30 degrees as their heating systems cycled on and off, Larsson's combination of sealed construction and earth-tempered ventilation maintained interior conditions within a narrow range. His fuel consumption during a week when outside temperatures averaged -5 degrees totaled less than half a cord of wood, compared to the cord and a half that Samuel Morrison burned in his conventional cabin during the same period. Community reaction to the buried tunnel ranged from bewilderment to outright suspicion. Crawford declared the excavation work a waste of effort that violated natural principles of building construction. Several neighbors worried that underground passages might undermine property drainage or attract unwanted wildlife. The territorial land agent, returning for his winter inspection, questioned whether such modifications might violate homestead improvement requirements that emphasize standard agricultural and residential development. Even with earth-tempered ventilation solving the fresh air challenge, Larsson recognized that his cabin's thermal performance remained vulnerable to a fundamental weakness that affected every structure in the settlement. Standard frontier construction treated floors as simple structural platforms, typically consisting of rough sawn planks laid over log joists with minimal attention to heat retention or thermal stability. During cold nights, these wooden floors became conduits for heat loss, conducting warmth directly into the ground below and creating cold zones that no amount of stove heat could effectively warm. Families throughout the Black Hills territory complained of persistently cold feet and drafty conditions near floor level, even when their cabins felt adequately heated at shoulder height. The thermal dynamics of conventional floors created a daily cycle of energy waste that compounded fuel consumption problems. During daytime hours, when stove fires ran hot and solar gain through windows added warmth, heated air rose toward the ceiling while cold air settled near the floor, creating temperature stratification that left living zones uncomfortable despite significant fuel investment. At night, when fires died down or families banked their coals to conserve wood, the wooden floors rapidly conducted stored heat into the cold ground below, causing interior temperatures to plummet within hours of reduced heating activity. Larsson's solution drew from thermal mass principles he had observed in both native winter shelters and Norwegian building traditions. During his trapping expeditions, he had noticed that earth-sheltered lodges maintained more stable temperatures than above-ground structures, even when their heating fires burned at lower intensities. The ground itself seemed to store warmth during active heating periods and release it gradually during cold hours, creating natural thermal regulation that reduced fuel demand significantly. His grandfather's stone and timber houses in the Hardanger Mountains had incorporated similar principles, using thick masonry floors and walls that absorbed heat during the day and radiated it back during cold nights. Construction of Larsson's earthen floor began in early October, requiring excavation of the existing ground surface to a depth of 12 inches below the planned finish level. He removed approximately 8 cubic yards of soil from the cabin's interior footprint, grading the excavated area with a slight slope toward drainage points that would prevent water accumulation beneath the thermal mass. The foundation layer consisted of 6 inches of graded gravel, carefully leveled and compacted to provide stable support for the heavy earthen materials that would follow. The thermal mass itself combined locally available materials in proportions that balanced heat storage capacity with structural integrity. Larsson mixed clay-rich soil from a deposit he had identified near Rapid Creek with chopped prairie grass, adding water to achieve a consistency that would pack solidly without excessive shrinkage during drying. The mixture required approximately 2 tons of clay soil, 400 pounds of dried grass fiber, and careful attention to moisture content that would allow proper curing without cracking. He laid the earthen mixture in 4-inch lifts, compacting each layer thoroughly before adding the next to eliminate air pockets that would reduce thermal conductivity. The finished floor measured 4 inches thick throughout the cabin's interior, creating a thermal mass that weighed approximately 15 tons and possessed enormous capacity for heat storage and release. Larsson sealed the surface with a mixture of pine pitch, beeswax, and fine clay that created a durable, water-resistant finish suitable for daily foot traffic while maintaining the thermal properties of the underlying mass. The sealed surface prevented dust accumulation and allowed easy cleaning while preserving the floor's ability to absorb and radiate heat efficiently. Testing during November's temperature fluctuations revealed thermal behavior that contradicted conventional wisdom about heating systems and fuel efficiency. When Larsson maintained a moderate fire throughout a cold afternoon, alcohol thermometers positioned at floor level registered steady increases that continued for hours after the fire had died to coals. The earthen mass absorbed heat energy during active heating periods and released it gradually over 8 to 10 hour periods, maintaining floor surface temperatures of 40 to 45 degrees Fahrenheit, even when interior air temperatures had dropped into the 30s overnight. The thermal performance became even more pronounced when Larsson added earth burming to the cabin's north and northwest walls. Using soil excavated during floor construction, supplemented by additional material from a nearby hillside, he built berms that rose to windowsill height and extended 3 feet from the wall base. The berming required approximately 12 cubic yards of soil, carefully graded and compacted to prevent settling while providing wind protection and thermal insulation to the most weather-exposed portions of the building envelope. Installation of the berms demanded attention to drainage and moisture control that conventional cabins rarely addressed. Larsson created a drainage layer of coarse gravel between the berm and his cabin walls, preventing water accumulation that could cause foundation problems or promote wood rot. He sloped the berm surfaces away from the building to direct precipitation toward drainage areas and installed simple gutters made from split logs to channel roof runoff away from the bermed areas during spring thaw periods. The combined effect of earthen floor thermal mass and protective berming became apparent during December's first severe cold snap when nighttime temperatures dropped below -10 degrees Fahrenheit for 5 consecutive nights. Interior measurements showed that floor temperatures remained above 40 degrees throughout the cold period, while wall surfaces protected by berming stayed 8 to 12 degrees warmer than exposed wall sections. The thermal stability eliminated the dramatic temperature swings that plagued conventional cabins, creating comfortable living conditions that required significantly less fuel input to maintain. Fuel consumption data from the December cold spell provided quantitative evidence of the thermal mass system's effectiveness. Larsson burned 3/4 of a cord during a week when exterior temperatures averaged -8 degrees, compared to the 2 1/4 cords that neighboring cabins required during the same period. More importantly, his interior temperatures never dropped below 38 degrees during overnight periods when fires were banked, while conventional cabins regularly experienced interior temperatures in the mid-20s when heating systems received minimal fuel input. The performance attracted attention from unexpected sources within the settlement. Hans Miller, an immigrant carpenter who had arrived from Bavaria the previous spring, examined Larsson's floor construction with professional interest and declared it superior to anything he had seen in frontier building. Muller possessed knowledge of European masonry heating systems that used thermal mass principles, and he recognized the technical sophistication behind what some neighbors dismissed as unconventional experimentation. Larsson's successful integration of earth-tempered ventilation and thermal mass systems created an unforeseen complication that threatened to undermine the entire project during the spring thaw of 1880. As ground temperatures rose and snowmelt saturated the soil around his buried tunnel, moisture began accumulating inside the ceramic pipe sections, despite their glazed surfaces and carefully planned drainage. Condensation formed where warm, humid air from the cabin met cooler surfaces within the underground passage, creating ideal conditions for mold growth and potential air quality problems that could make his innovative ventilation system worse than useless. The moisture challenge revealed itself gradually through subtle changes in air quality that conventional cabin construction never had to address. During late March, Larsson noticed a musty odor emanating from his floor-level air intake that grew stronger during periods of high humidity. Water droplets appeared on the interior surface of his wooden intake grate, and dark stains began forming on the cabin's north wall near the tunnel opening. More concerning, his family began experiencing respiratory irritation that seemed connected to extended time spent in the sealed cabin environment, suggesting that his carefully engineered air supply might be delivering contaminated rather than fresh air. Investigation of the tunnel interior revealed the scope of the problem and its potential consequences for long-term system viability. Using a series of candles on long wooden handles, Larsson explored the buried passage and discovered standing water in several low spots where his original grade had proven inadequate. Organic matter, including dead insects, decomposing leaves, and accumulated dust, had mixed with the trapped moisture to create conditions that supported bacterial and fungal growth. Without intervention, the entire tunnel system risked becoming a source of contaminated air that would make his sealed cabin environment dangerous rather than comfortable. Larsson's solution drew from traditional food preservation and root cellar construction techniques that immigrant families had brought from northern European climates. During conversations with Hans Müller about European building practices, he learned that successful root cellars in Bavaria and Norway incorporated specific drainage systems designed to handle ground moisture while maintaining air circulation. These underground storage areas use sloped floors, gravel drainage beds, and carefully positioned weep holes to direct water away from air passages, while preventing the stagnation that encouraged decay and contamination. Renovation of the tunnel system required excavating and rebuilding sections where drainage had failed, work that proved even more challenging than the original construction. Beginning in April of 1880, Larsson reopened the tunnel at 3 locations where water accumulation had been most severe, removing the existing pipe sections and regrading the trench bottom with a more aggressive slope of 2.5 degrees. He installed a continuous drainage bed consisting of 6 inches of graded gravel beneath the pipes, extending the gravel layer 6 inches beyond the pipe diameter on all sides to create a comprehensive drainage envelope. The enhanced drainage system incorporated weep holes and collection chambers, positioned at strategic intervals along the tunnel length. Larsson excavated small chambers at the 2 lowest points in the tunnel route, filling them with coarse gravel and connecting them to surface drainage ditches that would carry away accumulated moisture during wet periods. Each chamber measured 2 feet square and 18 inches deep, providing sufficient volume to collect and redirect substantial amounts of groundwater without compromising the air passage itself. Installation of the improved system demanded materials and techniques unavailable through standard frontier supply channels. Larsson fabricated additional ceramic pipe sections by working with a potter in Deadwood who could fire clay tubes to his specifications, creating pieces with thicker walls and more durable glazes than the original installation. Where ceramic pipes remained unavailable, he used sections of thick-walled maple logs, boring 4-inch diameter holes through their centers and treating the interior surfaces with a mixture of pine tar, linseed oil, and powdered lime that would resist moisture absorption while preventing organic growth. The renovated tunnel incorporated a systematic flushing protocol designed to prevent air stagnation and moisture accumulation during periods of varying weather conditions. Larsson installed adjustable dampers at both the intake and outlet ends of the system, allowing him to create controlled airflow that would clear stagnant air and excess humidity on a regular schedule. During dry, windy days, he opened both dampers fully to create maximum air circulation through the tunnel. During wet or calm periods, he partially closed the intake damper while leaving the outlet open, creating slower air movement that prevented moisture accumulation without overwhelming his cabin's thermal control. The air quality management system included filtration components that addressed contamination concerns while maintaining efficient airflow. Larsson constructed intake filters using layers of coarse cloth, dried moss, and charcoal that would remove dust, insects, and organic particles before air entered the tunnel system. The filters required replacement every 6 to 8 weeks, but they effectively prevented organic matter accumulation that had created conditions for bacterial and fungal growth during the system's first winter of operation. Testing during the summer months of 1880 demonstrated the effectiveness of the moisture control improvements and established protocols for long-term system maintenance. Humidity measurements taken inside the tunnel showed levels consistently between 40 and 50%, well within the range that prevented mold growth while maintaining comfortable air quality. Interior cabin humidity remained stable at approximately 45% even during periods of high outside humidity, compared to levels of 60 to 70% that neighboring cabins experienced during humid weather periods. The enhanced system's performance during autumn's first significant rainfall provided conclusive evidence of the drainage improvement's effectiveness. Despite 3 consecutive days of heavy precipitation that saturated the soil throughout the settlement area, Larsson's tunnel remained dry and free of standing water. Air quality measurements showed no increase in humidity or contamination levels, and the musty odors that had plagued the system during spring thaw did not return even during extended periods of wet weather. Community response to Larsson's renovation work reflected growing recognition that his experimental systems might offer practical solutions to widespread frontier building problems. Several neighbors who had initially dismissed his innovations began asking detailed questions about drainage techniques and moisture control methods that could be applied to their own root cellars and food storage areas. The territorial land agent, observing that Larsson's cabin remained structurally sound and problem-free, while several conventional cabins showed signs of foundation moisture problems, admitted that unconventional building methods might deserve serious consideration rather than automatic rejection. Hans Müller, whose carpentry expertise had proved valuable during the renovation process, declared that Larsson's moisture management system exceeded anything he had encountered in European construction. Müller began documenting the techniques with the intention of incorporating similar approaches into future building projects throughout the settlement, suggesting that innovative drainage and air quality control methods might become standard practice rather than experimental curiosities. The winter of 1881 delivered the ultimate test of frontier building methods when a high-pressure system stalled over the northern plains for 3 weeks, bringing sustained cold that exceeded anything in territorial weather records. Beginning January 15th, nighttime temperatures dropped below -20 degrees Fahrenheit and remained there for 14 consecutive nights, with several readings reaching -35 degrees during clear, windless periods that allowed maximum radiative cooling. Daytime temperatures failed to rise above -10 degrees for the entire duration, creating conditions that pushed conventional cabin heating systems far beyond their design limits and revealed structural vulnerabilities that milder winters had masked. The extreme cold exposed fundamental weaknesses in standard log construction that normal temperature variations had never stressed sufficiently to cause failures. At the Morrison homestead, the single-wall log cabin developed separation joints of up to 3 inches as the wood contracted beyond its elastic limits, creating gaps that no amount of chinking could seal effectively. The structural movement damaged the stone chimney foundation, allowing cold air infiltration that made the fireplace draw poorly and filled the cabin with smoke during critical heating periods. By the 8th day of the cold snap, interior temperatures had dropped so low that water in cooking pots froze solid within 2 hours of being removed from direct stove heat. Conventional cabin roofing systems proved equally vulnerable to the prolonged stress of extreme temperatures, combined with heavy snow loads that accumulated throughout the cold period. The Henderson family's cabin suffered catastrophic roof beam failure when frozen. Moisture within the wood structure caused splitting and joint separation that compromised the entire framework. Snow infiltration through damaged roofing created interior ice accumulation that made large portions of their living space uninhabitable, forcing the family to crowd into a single corner near their stove, while structural damage worsened daily. Food preservation challenges during the extended freeze revealed another critical weakness of standard frontier building approaches. Families throughout the settlement discovered that their root cellars and food storage areas, adequate during normal winter conditions, could not maintain temperatures above the critical threshold where preserved foods remained viable. The Crawford family lost their entire supply of root vegetables when storage area temperatures dropped below 20 degrees, turning potatoes, carrots, and turnips into frozen masses that spoiled immediately upon thawing. Preserved meats suffered similar damage as extreme cold caused salt, cured products to crack and develop ice crystals that destroyed their texture and preservation qualities. Water supply systems designed for typical winter conditions failed completely under the sustained extreme cold, creating survival crises that threatened entire families. Wells froze to depths never before experienced in the territory, and hand pumps became inoperable when mechanical components seized from frost penetration. The Mueller family was forced to melt snow for all water needs when their wellhead froze solid, and attempts to restore flow using heated tools proved insufficient to clear the blockage. Livestock watering became impossible at most homesteads, forcing families to choose between letting animals die of dehydration or exhausting precious fuel reserves to melt sufficient snow for basic animal survival. Larsson's integrated system faced the same brutal conditions, but responded with performance that demonstrated the cumulative effect of his multiple thermal management strategies working together as a coordinated whole. Interior temperature measurements throughout the cold period showed remarkable stability, with readings never dropping below 42 degrees Fahrenheit, even during the coldest exterior nights and without continuous stove operation. His earthen floor thermal mass absorbed heat during brief afternoon solar gain periods and radiated stored energy throughout the long nights, maintaining surface temperatures that prevented floor-level cold zones from developing. The earth-tempered ventilation system proved crucial during periods when fuel conservation became critical for long-term survival. While neighboring families faced the impossible choice between maintaining air quality and conserving precious cordwood, Larsson's tunnel continued delivering fresh air pre-warmed to 45 degrees, even when exterior temperatures reached their most extreme readings. The system allowed him to operate with minimal stove firing, while maintaining breathable interior air, reducing his fuel consumption to approximately 1 cord during the entire 3-week period compared to the 4 to 5 cords that surviving conventional cabins required. Food preservation within Larsson's stable thermal environment succeeded where traditional storage methods failed catastrophically. His root vegetables remained flexible and edible throughout the cold snap, stored in areas where consistent temperatures above freezing prevented cellular damage that destroyed his neighbors' food supplies. Preserved meats maintained their integrity without the cracking and ice crystal formation that ruined similar products in conventional storage areas. Water stored in containers near his earthen floor remained liquid and available for cooking and drinking without the constant fuel expenditure that snow melting demanded from other families. The performance differential became undeniable when neighboring families began seeking shelter and assistance during the crisis period. The Henderson family, their cabin rendered partially uninhabitable by roof damage and structural failure, moved temporarily into Larsson's stable environment where consistent temperatures and fresh air provided relief from the survival conditions they faced in their own dwelling. The Crawford children spent daylight hours in Larsson's cabin to escape the dangerous cold levels that persisted in their family's conventional shelter, even with continuous stove operation. Community attitudes toward Larsson's experimental methods shifted dramatically as the crisis demonstrated practical superiority over accepted building wisdom. Hans Muller, observing the structural stability and thermal performance that kept Larsson's family safe and comfortable while conventional cabins failed around them, declared that standard frontier building practices were inadequate for the realities of Northern Plains climate. Muller began documenting specific construction techniques with the intention of incorporating earth thermal principles into future cabin designs throughout the settlement. The territorial land agent, witnessing the performance comparison during his emergency winter inspection tour, officially noted that innovative building methods had demonstrated measurable advantages over standard practices during extreme weather conditions. His report to territorial administrators recommended investigation of earth-coupled heating and ventilation systems as potential improvements to standard homestead construction guidelines, marking the first official recognition that conventional frontier building wisdom might benefit from systematic revision. 2 families on the Eastern Ridge began planning earth tunnel installations for the following construction season, requesting detailed guidance from Larsson about excavation techniques, material specifications, and thermal mass integration. Samuel Morrison, whose own cabin had nearly become uninhabitable during the cold snap, approached Larsson about retrofitting his existing structure with earth burming and thermal mass improvements that might prevent similar failures during future extreme weather events. The crisis established earth thermal management as a proven alternative to fuel-dependent heating systems, while revealing fundamental limitations in conventional frontier building approaches that normal winter conditions had never exposed sufficiently to drive systematic improvements.